Hello everyone, I am recording an alternate version of video 35. In video 35, the original version, I described how to solve system of ODEs using an equivalent of method of elimination when we were solving systems of equations in algebra. The goal for this video is to describe the technique of substitution to solve systems of differential equations. And personally, I find this to be a slightly easier method. And so far, in all the practice and research that I've done, I have yet to find a problem where elimination is easier than substitution. So this is just my personal taste. Substitution is better. The idea of solving an ODE by substitution is very similar to the method of solving an algebraic equation by substitution. You had examples something like, 4x plus 5y equals 7, x minus y equals 3, and you took one of those equations and you isolated one of the variables and expressed x in terms of an expression containing only y, or vice versa. You could alternatively isolate y and express y in terms of something that contained only x. When you did that, you unlocked the ability to substitute that expression into whichever equation you had not yet used, to transform that equation into something that contained only one variable, only y in this case. In the differential equations world, method of substitution works almost exactly the same way. The idea is to completely isolate one of the output variables in one of the equations that you are given, and then plug that expression into the other equation Now your equation, if everything has gone correctly, should only have one output variable in it. So then you can solve for the value of that output variable, similar to how we would be able to solve this equation after substitution for y. To demonstrate the technique, let's consider the following abstract example. We have got x prime equals negative y plus t, and y prime, this is dy dt, y prime equals positive x minus t. So let's go ahead and rewrite this slightly in a little bit of a nicer notation. What I'm going to do now is I'm going to take one of these equations and completely isolate one of the output variables. For example, it looks like if I start with equation number 2 and add t to both sides, that I get the fact that x in reality is equal to y prime plus t. So I've completely isolated x, and I have expressed it in terms of the other output variable y and the input variable t. Having achieved that, I can now take this expression and plug it back into whichever equation I have not yet used. And so now instead of x prime, I can write the quantity y prime plus t prime equals negative y plus t. If I apply that derivative to both terms using the sum rule and rearrange, then I get this non-homogeneous constant coefficients ODE in terms of the output variable y. So there are no x's here. And because there's only one output variable, second order constant coefficients non-homogeneous ODE, this is now something that we can solve using any of the techniques that we've established up to this point. So for example, we can start by finding yc, and yc would be found by setting this equation equal to 0. It's constant coefficients, so we would pass to this auxiliary equation, which has these complex roots, And so our yc would be equal to c1 cosine of the input variable t plus c2 sine of the input variable t. That would be our complementary function. The next thing that we would do is we would find a particular solution. And because we have constant coefficients on the left and a polynomial on the right, we can use method of undetermined coefficients and guess that yp is also a polynomial of degree 1. And be careful, once again, we need to remember that t is the input variable in this problem. We cannot use x for the input variable because x is being used for the other output variable in this problem. Now for a linear equation, the second derivative, the concavity, is 0. So if I plug that guess into my differential equation, I get a t plus b equals t minus 1, which forces a to be 1 and b to be minus 1, which forces y particular, in this special case, to be exactly equal to the t minus 1 on the far right side of our original problem. And so from that, we get our general solution. The general solution for y is equal to c1 cos of t plus c2 sine of t plus the particular solution t minus 1. Now, we're not done yet, right?
You're not done yet.
It remains for us to find the value of the other output variable, x of t. Now, just like when you're solving an algebraic equation, the easiest way to find the value of the other variable, x of t, is to use the equation that you got when you started your substitution and plug in the formula for y that you just obtained. Here, we are saying that the x is equal to y prime plus t. So in our problem, the x would be equal to the derivative of the y formula that we just found, big prime for derivative, and then that plus t on the outside. So, calculating that derivative, looks like I'm going to get minus c1 sine of t and plus c2 cosine of t. The derivative of plus t is 1. The derivative of minus 1 vanishes, and then I have that plus t term in the back. So, these two equations, this one and this one, together make up the answer to this problem. Method of substitution, very, very similar to what you saw back in the days of algebra. For our second example, let's go ahead and return to this problem that we set up in video 34, corresponding to the case, of mixtures in multiple tanks. Now, previously, I don't know what I was thinking. I decided that I was going to carry subscripts around like I was some kind of physics professor or something. Instead of using x sub a and x sub b, I think I've decided that I would prefer to just use a and b. So let's go ahead and solve this equation using the method of substitution. And to that end, let me go ahead and rewrite this expression in a slightly different way. For the sake of my sanity, I think I'm going to go through and clear these fractions. So maybe I'll hit the first equation with a 50 and the second equation with a 25. That should do it. This gives me 50 copies of the derivative of a equals b minus 50 divided by 25 times 2, 4a, and below 25b equals 2a minus 2b. So now I get to take one of these equations and completely isolate one of the variables. And the one that looks like it'll probably be the easiest to work with is this one. If I take this equation and add 4a to both sides, then that will completely isolate the output variable b. b is equal to this expression, which does not contain any b's in it, only contains a's. Now, if I substitute this expression, that's a b prime, if I substitute this expression into equation number 2, let's see what we get. 25 copies of the derivative of b. The derivative, in other words, of 50a prime plus 4a equals 2 copies of a minus 2 copies of b, where b once again is 50a prime plus 4a. Now let me go ahead and simplify that expression. If I apply the sum rule to this first guy in the bracket, that'll be 50 copies of 2 derivatives of a plus 4 copies of 1 derivative. And let me go ahead and distribute. I get 1250a double prime plus 100a single prime, excuse me, this guy is negative 8a, is equal to negative 6a minus 100a prime. If I bring everything to one side to rewrite this as a homogeneous ODE and divide everything by the common factor of 2, then that brings me here to this second order homogeneous constant coefficients ODE. To solve this, we can go ahead and rewrite this, giving us the auxiliary equation 625r squared plus 100r plus 3 equals 0, which, if I recall correctly, factors as 25r plus 1, 25r plus 3 equals 0. So that would mean that r was equal to negative 1 over 25. R was equal to negative 3 over 25. So our A of t is equal to the solution to this homogeneous ODE, c1e to the first root plus c2e to the second root. Now let's go ahead and find b, remembering this equation at the top, which told me that b was the same thing as 50 copies of a prime plus 4 copies of a. So 50 copies of a prime looks like 50 copies of the derivative of the expression that we found in the previous line. It's a terrible bracket. Alrighty, that's a better bracket. And then 4 copies of a, the original a. It looks like it is going to work out to be 2 copies of c1 e to the negative 1 over 25t and negative 2 copies of c2 e to the negative 3 over 25t. So these are the formulas which are applicable to A of t and B of t, which will predict the amount of salt in the tank at any given time. But these formulas are useless without specific values of C1 and C2. Now, to get those two unknowns, we're going to need 2 equations. And those 2 equations are furnished by the initial conditions that we found / were given from the problem, which is that initially tank A contained 25 pounds of salt and tank B contained no pounds of salt because it had pure water. So let's use those initial conditions down below to say, first of all, that B of 0, which is equivalent to 2C1 minus 2C2, must be 0. And therefore, it seems that C1 and C2 must be equal. If I plug 0 into the A of t formula, then I get C1 plus C2, which is supposed to be equal to 25. Since C1 and C2 are equal, they must both be equal to 1/2 of this 25. And from that, we get our formulas for A of t and B of t. I'm going to shamelessly copy-paste, going in and replacing C1 and C2 with 25/2. We get our formulas for A of t and B of t. So that is the method of substitution as applied to solve systems of differential equations.